Hello everyone. Today I would like to present our research titled Geometric Mesh Structure Design and Efficiency Analysis for Enhancing Fog Collection Performance of High Voltage-Based Fog Harvesters. More than 1 billion people still lack access to safe drinking water. In many dry coastal regions, rainfall is low but ocean fog is frequent, which makes fog harvesting a promising alternative water source. However, traditional passive fog collectors using metal meshes are very inefficient. Most droplets simply pass through the openings, so collection rates often stay around 1 to 2% and rarely exceed 10% even in laboratory settings. Recent studies, including work from MIT, have proposed applying high voltage to actively pull droplets. A corona discharge charges the droplets, and these charged droplets are attracted toward the mesh. This electrostatically assisted approach significantly increases fog collection. Even with high voltage, mesh geometry still plays an important role. When the wires are too close, the electric capture regions overlap and the system saturates. When the wires are too far apart, weak field regions appear and droplets escape. Our research question is which mesh geometry maximize fog collection efficiency? Our hypothesis was that the key factor would be spacing between wires defined by the hole width and the hole height. Here is the overall experiment process. It includes 4 main steps: designing the high voltage generator, designing and installing the mesh, making and testing the fog collector, and finally implementing the fog collection experiment. To investigate this, we first built a high voltage generator using a Cockcroft-Walton circuit, increasing the voltage to several kilovolts with capacitors and diodes. For the meshes, we used a zinc mesh with 0.6 by 0.6 centimeter holes as the base. We cut 17 by 16 hole pieces and modified them to create rectangular openings from 1 by 1 to 5 by 1 in both directions. This allows us to systemically change spacing while keeping the material constant. For the fog source, we initially used a styrofoam collector body and later improved it with 3D printed parts. A household humidifier generated the fog, which flowed toward the mesh, and we measured the collected water over 3 minutes using a petri dish or a beaker. We kept environmental conditions as consistent as possible. Across all trials, the independent variables were the use of high voltage and the mesh geometry. The dependent variable was the mass of the water collected. Let me now explain the results. First, we tested all meshes without high voltage. As hole size increased, the collected water decreased. The 1 by 1 mesh collected around 0.011 grams, while larger openings like 1 by 4 or 1 by 5 collected only 0.002 to 0.003 grams. With larger openings, droplets simply passed through the mesh. Next, we applied high voltage. Under these conditions, water collection increased dramatically for all meshes, but the difference between geometries became clearer. Meshes such as 1 by 2, 1 by 3, 2 by 1, and 3 by 1 performed the best, and 1 by 3 and 3 by 1 showed the highest overall efficiency. Very large openings were less effective because droplets escaped through weak field regions. This pattern can be explained by the balance between saturation and field coverage. Dense meshes like 1 by 1 experience saturation, while very open meshes leave large regions with weak electric fields. Intermediate meshes maintain strong electric fields across the gaps and avoid excessive overlap of capture regions. To interpret the results, we defined Q-off as the water collected without high voltage, delta QEL as the additional water collected due to electrostatic effects, and Q-on as the total water collected under high voltage, which equals Q-off plus delta QEL. We found that the measured Q-on values fit well with a function of form A plus B over S, where A is 0.002 and B is 0.0103. We then defined Rs as Q on S divided by Q on 1, and its meaning is the efficiency normalized to the 1 by 1 mesh under high voltage. This ratio followed a quadratic trend, and the optimal spacing value, S, was approximately 2.6, which corresponds closely to the peak performance of meshes like 1 by 3 and 3 by 1. In conclusion, we demonstrated that high voltage spacing charge assisted fog collection greatly improves water harvesting. Mesh geometry is a key factor. Neither very dense nor very open meshes are efficient. Instead, intermediate designs such as 1 by 3 or 2 by 1 show the best balance and highest efficiency. In future work, we plan to test more mesh geometries, vary fog flux conditions, and scale up the device to create practical, low-energy fog harvesting systems for real-world, fog-rich, water-scarce regions. The reference articles are shown on the slide. Thank you for listening.